Welcome everyone to this session of the AI for Net Zero webinar series. I'm Sarah and I will be your chair today, and I'm joined in the studio by Koyer from Northumbria University. So this webinar series is designed to bring together experts, innovators and enthusiasts from both the artificial intelligence and sustainability domains, with an overarching goal to accelerate progress toward net zero targets. So we aim to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. Today it's our pleasure to host Dr. Hossein Mohammadi, who is currently a lecturer in statistics and data science at the University of Exeter. Prior to this, he completed his PhD in applied mathematics at the École des Mines de Saint-Étienne in France, and held two postdoctoral research fellow positions in the mathematical departments at the University of Exeter. His research primarily focuses on developing methods for quantifying uncertainty in computationally expensive numerical models, particularly those used in climate and environmental predictions. His work includes contribution to Gaussian process simulation, adaptive design of computer experiments, Bayesian optimization, and uncertainty and sensitivity analysis. Today, he will talk about sequential design of for emulating costly computer codes. So please join me in welcoming him. Feel free to engage anytime in the discussion by writing your question in or comments in the YouTube chat. We will host a Q&A at the end of the talk. So Dr. Hossein, thanks for being here with us today, and the floor is yours.
Oh, thank you very much, Sarah, and thank you for the nice introduction. My name is Hossein, and today I will present my work on adaptive design of computer experiments. And this is the outline of my talk. At the end, I talk about At-Risk project, which is part of AI for Net Zero. Okay, let's start off with the context of this talk. As you know, today computer models, also known as simulators, are widely used in many real-world applications, ranging from climate change to healthcare. Their applications are especially important in applications where conducting physical experiments is costly or even impractical. A computer model typically takes a set of input parameters denoted by boldface X and produces some output quantity of interest denoted by f of x. Okay, and a computer model reproduces real-world phenomena using complex mathematical equations implemented as computer code. These mathematical equations are often ODEs or PDEs. However, from a statistical perspective, we consider computer models as black box and try to approximate the input-output relation within the model. The problem with computer model is that they are computationally expensive often because they are based on complex mathematical equations, as I mentioned. This restricts us to have access to many model evaluations. For example, in order to conduct sensitivity analysis or uncertainty quantification, which are essential analysis for the development of a computer model, we need to run the model for many times. And this becomes infeasible if the model is computationally expensive. A common approach to tackle this problem is to approximate such complex models with cheap to evaluate statistical models known as meta models or surrogate model. They are constructed based on only a limited number of model evaluations. Especially in this work, we address this challenge using adaptive design of computer experiments, DOE, and Gaussian process emulators, which is a type of surrogate models. And I will explain both of these concepts in the next slides. Okay. A design of computer experiments refers to the process of selecting uh, uh, a couple of input values from the space of from our parameter space to construct an accurate emulator for the model output f of x, of course, using the minimum number of model evaluations because they are expensive. Here you see a two-dimensional example where we have x1 and x2 as the input, and we have and the black dots represent the points we have selected using a sampling plan. Okay, then we run the simulators at these points and obtain the corresponding outputs, these points, and then we fit our Gaussian process emulator to these limited data points. And since an emulator is very fast, we replace these approximations with the true model, with the true simulator, and then conduct our statistical analysis based on our emulator, which save a lot of time. Okay. In general, there are two design strategies. One strategy is called one shot, where we select all the samples in advance of the constructing the emulator. The most famous approach in this regard is called Latin hypercube sampling. I believe many of you are familiar. However, there is a problem with this approach, and the problem is that since we set the number of model evaluations in advance of building the emulator, it may result in under or oversampling and wasting computational resources. What does undersampling or oversampling meaning? It means that, for example, you set a number of model evaluation, let's say 100, but maybe you don't reach the acceptable level of accuracy with the with your emulator with 100 evaluations. So you need to do again this sampling approach. Or oversampling means that you have sampled a lot of points, but your emulator has already reached an acceptable level of accuracy. On the other hand, an adaptive design doesn't suffer from this problem, and I'll explain more this approach. In an adaptive design, we select the samples sequentially to improve our emulator. Of course, since this is a sequential process, we can stop expensive sampling as soon as we reach a desired accuracy. So with this, we can save our computational resources. Okay. An adaptive design typically relies on an acquisition function, alpha x, and we select a new point based on optimizing this acquisition function. Why we use this acquisition function? Because we are in the dark, but we want to find the most informative sample and add it to our design. Okay, so ideally we need to find the optimum balance between exploration and exploitation, and an acquisition function provides a balance between these two concepts. And exploration means that sampling in regions that have not discovered yet. For example, areas that we don't have any sample that represent the underlying function. Exploitation means that we have already sampled in regions, and we found that it's a promising region. So we want to sample more point at that region. Okay, so again, and we need an acquisition function because it provides a trade-off between exploration and exploitation. And in fact, all adaptive design approach are based on proposing a good acquisition function. Next slide. Uh, the next concept is Gaussian processes, which is which is our emulator, and we use it to approximate our models. A Gaussian process, denoted by Z naught X, is a distribution over functions. It extends the multivariate normal distribution to infinite dimensions, if that makes sense for you. And it helps us because we, at any point, we have a normal distribution, and this and any finite samples of Gaussian process values also follows a multivariate normal distribution. These are interesting properties, and we use in our adaptive sampling methods and other adaptive methods such as Bayesian optimization. However, a Gaussian process is fully specified with only two functions. One is its mean function. Please note that now we face functions, not, for example, mean covariance matrix or point mean estimate. So the mean is denoted by m naught and the covariance function with k naught. This covariance function plays a critical role in Gaussian processes. It takes two input values, x and x prime, and returns the covariance values between the Gaussian process values at x and x prime. In this picture, you see three realizations of a Gaussian process, but with different covariance function. So in this picture, this gray line represents the mean function. In the Bayesian statistics, it's called prior mean. And we have four realizations. These realizations are based on a squared exponential covariance function, which gives us very smooth samples of random functions. However, if we believe that the underlying function we want to emulate is not very smooth, we can use this type of Gaussian process where the realizations are not as smooth as a squared exponential covariance function. Yeah, and as you can see, for example, the covariance between the values of the Gaussian process at this location are less than or are less correlated than this case. Okay, and of course, K determines the regularity of Gaussian process sample paths. These are called sample paths. Okay, next slide. To do prediction with Gaussian process, we need training sets denoted by A, and it consists of n xi and fxi, I from 1 to n. So xi are obtained based on design strategy, and then we evaluated our model at those locations, and we have obtained this training set. The GP prediction follows Bayesian rule to obtain the posterior distribution of the function. It follows Bayesian rule, and I denote by z and x the posterior distribution of this z naught conditional on the training set A. So the prediction, which is this thick line, is obtained by taking the mean of this conditional process and the corresponding variance, predictive variance, again, is the posterior variance of this conditional distribution. One of the advantage of Gaussian processes is that we have closed form expression for this posterior mean and posterior variance. Okay, and the posterior mean, denoted by mnx, is the expected value of the posterior covariance function, which with this closed form expression, and the same, the posterior variance at each point x is the variance of the posterior covariance, posterior Gaussian process, which with this expression. Uh, uh, I really don't want to focus on these expression. Just we use a lot the posterior mean and the posterior variance in our method. Just please, yeah, it's good to remind these two uh, notations. Uh, Yn is the objective function values or the model output at n locations. This boldface k is a vector, contains the covariances between z at x and all the n observations, and this bold k is the covariance matrix between the between the Gaussian process values at n locations or at n observations. Yeah, this is the prediction and the associated uncertainty provided by a Gaussian process. Now I present my adaptive sampling criterion called VIGF, which stands for variance of improvement for global fit. VIGF is based on an improvement function, I of x, which is the squared difference between the posterior Gaussian process and the model output at the closest observed point. Maybe this is not clear, but if you please have a look at this picture. So we have a Gaussian process. This is our predictive mean with the associated uncertainty shaded area. And at, let's say, at x equal to 4, we have a normal distribution because it's a Gaussian process. And the closest sample point that we have already observed is this point. Okay, not this one or that one. Okay, this one is the closest. So this improvement function measures the difference between the Gaussian distribution at this location and the observed value x star 3 and fx star 3. Okay, so since this is a stochastic quantity, I of x is also stochastic, and we can obtain the moments of this quantity. Okay. We have shown that I of x follows a non-central chi-square distribution, and we can simply extract its mean and variance. If you are interested, please have a look at our paper, which explains more why this I of x follows a non-central chi-square distribution. As you can see, our acquisition function, which is the variance of I of x, is a combination of the posterior mean and posterior variance, sorry, and posterior mean. And in this expression, s squared n represents the exploration, and this quantity is the exploitation term. So in fact, we want to find the next sample where the distance between Gaussian distribution at any point and the closest observed sample has the largest variance. Okay, if that makes sense. And we found that these combinations provide a good or quite optimal combinations between exploration and exploitation. So let's say we have already n samples. The next sampling location denoted by xn plus 1, is obtained by maximizing VIGF. Okay, in this case, we have 5 sample points, and we have fitted our Gaussian process to this data. We can construct our VIGF, which is this shape, and we take the 6th sample where it is maximum. It's here. So the next sampling point would be here, and maybe in this picture you can see it's better. I have plotted VIGF in a different pictures, and yeah, it's the maximum is here. So we sample or evaluate our model here, and we add it to the existing data, and then we update our Gaussian process. Of course, we have a better prediction because with more samples, we have more data and our emulator becomes more accurate. And this process continues until a stopping criterion is met. Usually, the stopping criterion is the number of model evaluations that is affordable. Please, you can interrupt me at any point if you found something not very clear. Okay. I believe many of you may be thinking why not using expected improvement, the expected value of the improvement function. I mean, the expected value of I of x, that again can be expressed in closed form like this. However, it is found that using expected improvement for global fit tends toward local exploitation. Here is a good example, is a 2D example where the underlying function is a sum of 2 Gaussian functions. And as you can see, expected improvement puts all the new samples, which are red circles, in this area, while this area is unexplored. The black dots are the initial design, and again, the red circles are the sampling point obtained by expected improvement for global fit. While we found that our methods have a better coverage. In fact, we can see now the red circles can discover this area, and if you fit a Gaussian process emulator to all these data, we get a much better representation of this underlying function compared to EIGF. Okay. We have also extended our method to batch mode sampling. Batch mode sampling can be very useful, especially when we have access to parallel computing, because it can save the user time and reduces the whole clock time. The batch version of VIGF is quite simple. We call it pseudo VIGF or PVIGF, and it is obtained by multiplying VIGF by a repulsion function. And I will explain what a repulsion function is in the next slide. So again, using a batch mode sampling allows us to sample more than 1 points at each iteration. And it is very useful if we want to, we have access to parallel computing. What is a repulsion function? The repulsion function at any point x, and is denoted by RF, repulsion function, at any point x is defined as 1 minus correlation between the posterior Gaussian process at x and the posterior Gaussian process value at xu. What is xu? Xu is the point, we call it an updating point, is the point that we found it's informative, but we want to continue sampling without evaluating the model, which is expensive, at xu. So we want to have xu and continue sampling without referring to our expensive compute model. Okay, so how does it work? In fact, let's go back to our previous example. So we want to select this point, okay? We call it x6, okay? But we want to take more samples without running the model. Okay. Now I multiply my VIGF, which is in black, by this repulsion function, which is in green. As you can see, the value at now, please note that XU is X6. Okay. I want to sample more points and without evaluating the model at X6. So then the pseudo expected improvement, which is the red curve, becomes zero at X6, which is my updating point. But as we get farther from X6, it tends to 1, which is good because then we can quite uh, uh, reproduce our VIGF. Okay. And the next sampling location is obtained by maximizing PVIGF, which would be here. So it would be helpful, and we can continue this process. And next, for example, we multiply this PVIGF with another repulsion function, and we can continue sampling. Uh, I think looking at this algorithm can be helpful. So again, we have n sampling. We have already sampled n points, and as usual, we optimize VIGF to obtain xn plus 1. Now we can create PVIGF by multiplying a repulsion function at any point x. Now the updating point x is xn plus 1 times VIGF at x. Okay, for j from 2 to q in a loop, of course, q must be greater than 2. Okay, the next sampling location is optimized by is obtained by maximizing PVIGF at x. Okay, at any x. And then again, we multiply RF repulsion function. Now the updating point is xn plus j times PVIGF. Okay, we obtain a new PVIGF, and this process continues. Finally, we can obtain n plus 1, n plus 2 to n plus q without evaluating our model. Here, I show you some experimental designs, experimental results where I have compared VIGF with EIGF mice developed by Serge Gilas and his former PhD. We have already developed another design, adaptive design based on leave one out cross validation. I compare VIGF with this one as well, and mean squared error, and also Latin hypercube design. I have compared with all these adaptive design. However, the LHS is not adaptive. We have used 8 functions as model, the model I want to emulate, and with different dimensionalities from 2 to 7. The total budget means that the total number of model evaluation allowed is 30 times the dimensionality of the problem, and the size of initial design is three times dimension obtained based on Latin hypercube sampling. Okay, here is my results. On the x-axis, you see the number of function evaluations divided by dimension. Okay, it's from 1 to 30 because the total budget is 30. On the y-axis, I have normalized root mean square error, which is a measure of the distance between the emulator and the model. Of course, the smaller, the better. And here represent the function, the dimensionality of the problem. VIGF is in black, and if you can see, as the sampling process continues, VIGF constantly decreases, which is a good sign, and we can observe the same phenomenon in other experiments. And what we found is that the results obtained by VIGF is quite robust. For example, other methods, sometimes they work very well, but sometimes not. But VIGF, we found it it performs quite robustly. And each curve represents the median of 10 normalized root mean square error. In fact, we have used 10 different initial design of experiments, and we have obtained 10 different normalized root mean square error, and we take the median of them, and this curve actually represents the median. The other results are provided here. Again, we can see quite good performance by VIGF, the black one, compared to other method. And yeah, and again, with normalized root mean square error on the y-axis, F evaluations time the problem dimension on x-axis. Okay, and finally, I will present At3's project briefly. I have provided the link to this project here. So please, if you are interested, have a look at the web page of At3's. In a nutshell, At3's aims to use AI tools to support decision making regarding land use changes. This is in alignment with the UK government's goal to achieve net zero emissions by 2050. At3's has several themes such as adaptive design, data fusion, uncertainty quantification, model inversion, and different groups are working on these themes. Again, if you are interested, please have a look at this at the website of At3's. In the At3's project, we need to run a lot of expensive simulations regarding landscape decision. In this regard, using adaptive methods, especially VIGF, could be very useful for automating the emulation of such complex models. As part of this project, VIGF and other adaptive methods as well are implemented in our package called DGPSI. In this package, the adaptive methods are implemented based on both Gaussian processes and deep Gaussian processes. To be honest, I'm not an expert in deep Gaussian processes, so I won't comment on deep Gaussian processes. Just note that deep Gaussian processes can be helpful if we are emulating a model that is highly non-linear or highly non-stationary, because the standard Gaussian processes are developed to emulate stationary function. And if this property is not met, maybe Gaussian processes maybe is not an ideal tool to emulate your model. As an interesting example, I show you the results of emulating a six-dimensional engineering problem, which simulate the OTL push-pull circuit. And in this case, we found that using adaptive method, either VIGF or mice, with deep Gaussian processes can improve the performance of both methods significantly. Again, we have root mean square error here and iterations on the x-axis. The deep version of VIGF and mice, black and red, has a superior performance compared to using them with Gaussian processes. As you can see, we don't see much progress with Gaussian processes. And in conclusion, we found that adaptive design can offer a number of improvements over one-shot design. We propose a novel design criterion called VIGF for adaptive sampling. In addition, we propose the batch version of VIGF, which can be helpful to save the user time. Also, we have extended VIGF to the multi-fidelity modeling. I didn't present multi-fidelity modeling for the sake of time, uh, but there are many situations where we have several simulators that simulate the same quantity of interest, and we want to leverage information by lower fidelity model to create an accurate emulator for the high level, high fidelity model. So this is the multi-fidelity modeling. Again, I skipped, but if you are interested, please have a look at our paper. And we found that in most test cases, VIGF has a superior performance compared to the available methods. Uh, and here you can see the references I have used in this talk. Thank you very much for listening.
Thank you very much, Hossein, for your very interesting presentation. We will now open the floor for the Q&A. So I only encourage the audience to post their questions in the chat, and in the meantime, we will start with some from the studio here. So Goya, do you have any question, or do you want me to start?
Yeah. Thank you, Hossein, for that lovely presentation. Yeah. So, can you just have an idea, or can you just throw some light on some real world case studies which have been carried so far, means which have tried to reduce the cost of the simulations?
Yeah, that's a good question. In fact, yeah, we are in the process of developing or extending this method to real world applications. And I believe researchers, especially in at-risk project, will came across interesting results regarding reducing the computational time. Yeah, and yeah. However, in addition to the real world cases, it would be interesting to see the application of adaptive methods, for example, for sensitivity analysis and uncertainty quantification, and to see how useful the adaptive methods could be. Thank you.
Okay. Thank you. And also, like I've seen that you have used NRMSE, that is the normalized root mean square, as one of the matrices. So, apart from NRMSE, are there any further matrices from which we can measure the accuracy or the efficiency of the different adaptive strategies?
Yes, there are actually several methods, and again, that's a good question. Um, I haven't used, but you are right. It's always good to use different criteria to assess the accuracy of our methods. Especially, I believe using criteria that uses the uncertainty of the prediction to measure the accuracy of the methods could be beneficial, because root mean square error just takes into account the distance between the emulator and the simulator, not the uncertainty of the emulator. Yeah.
Okay. And like means as I found that this topic can be little bit aligned to even my topic, that is for increasing the resilience, because here we are using like more of a solar and wind energy, and they are like renewable DER, so they are like very non-linear in nature,
Mhm.
and even the solar is very intermittent. So can this adaptive strategy be used for the modeling, like weather modeling or some climate modeling?
Yeah, of
So,
course.
yeah.
Yeah, of course. And but I believe we need to take into account the noise in our observations. The current version of VIGF I have presented is for deterministic computer model, but when applying these methods and similar methods to real world data, we need to account for the noise in our observations. And I'm more than happy to collaborate with you if you think it's
Yeah, because this like the solar also follows the irradiance follows some Gaussian waveform, and so I think this Gaussian process and adaptive strategies can be aligned, and then yeah, we can work out.
Yeah, I have seen really papers dealing with this problem, and again, I'm keen to work on real world applications.
Thank you, Hossein.
Thank you.
Yep. I will have some question as well. So if I get it correctly, when you sampling a new point with your variance improvement approach, then you rerun the simulator, or you postpone the run of the simulator through the recursive function. So my question will be on the use of the recursive function. How do you ensure that your postpone of the simulator is not giving you oversampling point at some point? How do you manage to like postpone this simulator?
You are right.
And
Yes, yeah. In fact, you are right. If we, we our batch sampling, in our batch sampling, we select a lot of points. Yeah, it may result to oversampling. You are absolutely right. And I think more analysis is required. Really, it is missing. What is the optimal number that we can select at each iteration in order to avoid oversampling? I hope I could answer.
yeah. So in the like same line of questions, do you think it would be possible to incorporate in your acquisition function some prior knowledge about the computational cost of each sample point? I mean, especially when I'm thinking about 2D or 3D application case scenarios involving spatial temporal domain. So I guess like you won't be as cheap to evaluate your computational model in some heterogeneous areas and in more homogeneous one, for instance. So could you think about using some priors like this in the acquisition function?
I think so. Although I have never thought. It's a thank you. It's a good question. Thank you. And this is something that we need to work on. But at the moment, I haven't. Sorry.
Okay. No, really interesting
Thank you.
presentation.
Yeah, thank you very
So
much.
yeah, and I think like if you move to this kind of ideas, then you will have kind of a multi-objective function to deal with as
Oh
well,
yeah,
which
yeah,
is not your case right now. So
yeah,
I see some advantage of keeping it one objective
yeah,
function.
yeah. Thank you.
Good. Yep. Well, I don't see any question from the audience right now. So yeah, do you have some more?
I think I'm good. Yeah.
Okay. Yep. So I think we maybe can close the session.
Yes. So thank you, Dr. Hossein, for sharing your expertise today, and thank you all for joining us today. So we are looking ahead. We are excited to announce our next week's webinar. So we will have two speakers from the University of Exeter presenting on some really interesting topic. So we have Tristan Can, who will be presenting how does generative AI see climate change. So he will be exploring the challenges and opportunities of generative AI for climate visual journalism. And also we have Ville Inkin, who will be presenting assessing the impacts of protected areas on Bolivia's forest using machine learning and differences for casual identification. So we are awaiting to meet our new speakers for the next week. So thank you all for joining us. Have a lovely day.
Thank you very much. Right.
Thank you, everyone.
Thank you.